Hello again. In the last topic, we developed some rules that we could use to find derivatives of some functions. But we were quite limited in the types of functions that we could use to calculate derivatives. In this topic, we're going to build on what we've learned and develop a couple new techniques that we can use to find derivatives of more complex functions. The first that we'll develop is called the product rule, which we can use to find the derivative of a product of functions that are differentiable. So let's start by considering the example here. We want to find the derivative of h of x is x squared by x to the fifth plus 7. It might be tempting to just say, well, I know how to find the derivative of x squared, and I know how to find the derivative of x to the fifth plus 7. So the question might be, is h prime of x, is this equal to 2x, since that's the derivative of x squared, times 5x to the fourth, since the derivative of x to the fifth plus 7 is 5x to the fourth. All right, well now if we use a little bit of algebra, this would be the same as writing 10x to the fifth power. Now, I know that this is incorrect, but let's see an explanation of why it's incorrect. Using algebra first, we could have written h of x as equaling x to the seventh plus 7x squared, just applying the distributive property. Then differentiating, using what we've learned in the previous section, then h prime of x would be equal to 7x to the sixth plus 14x. Now, I know that this first step is correct from algebra, and I'm pretty sure this second step is correct from what we've learned in the previous section. And I see that this is obviously not equivalent to what I wrote over here in red, the 10x to the fifth. So I'm pretty confident that this is invalid. We cannot, if we see a product of functions and we wish to differentiate that, we cannot simply differentiate the first factor and multiply it times the derivative of the second factor. It simply doesn't work. So instead, let's develop a product rule. Let's assume that f and g are differentiable, and we want to find the derivative with respect to x of f of x times g of x. All right, well, let's apply the limit concept. This is the limit with h approaching 0 of f. Okay, so now we're treating this as our entire function that we're differentiating. So we would have f of x plus h times g of x plus h minus f of x times g of x. That's all in the numerator, and we divide that whole thing by h. Now, that's the limit definition. Unfortunately, there's nothing that we can really do here. We can't do any factoring. There's no, and we can't let h approach 0 immediately because it would then be an indeterminate form. So what we're going to do is we're going to use an algebraic trick here. We're going to add and subtract the same quantity in the numerator. And now, I didn't think of this. This is something that was developed a long time ago, and when I saw it the first time, I said, hey, that's pretty neat. So I learned the technique, and we're going to go with it from there. So the quantity that I'm going to add and subtract is this. I'm going to rewrite this. This is equal to the limit with h approaching 0. And so I'm going to leave the first term alone, f of x plus h, g of x plus h. Then what I'm going to do is I'm going to add and subtract. Well, subtract and add. I'm going to subtract and add the same quantity. And here's the quantity. I'm going to subtract f of x plus h times g of x. And I'm going to add back that same quantity, f of x plus h times g of x. And so effectively, I've added 0 here, which is completely legitimate, right? We're always allowed to add 0. And then I still have the minus f of x, g of x. And this is still all divided by h. You might say, well, why do this? Well, this particular quantity, if you notice, has now a factor in common with each of the original terms. Notice that if we compare the first and second terms, they have a common factor of f of x plus h. And if we compare the third and fourth terms, they have a common factor of g of x. So using some factoring, I can rewrite this as the limit with h approaching 0. And let's see, I'm going to write this as f of x plus h times g of x plus h minus g of x over h. All right, so that's taking care of the first two terms. Notice how I factored out the f of x plus h. Then what I'm going to do is I'm going to break up the limit into two limits, really. Now I have the limit with h approaching 0, and I'm going to factor out the g of x in the second grouping. So that's g of x times f of x plus h minus f of x over h. Now I'm going to use some properties of limits. I'm going to break up this first limit. Actually, I'm going to break up both of these limits into two limits. This is the limit with h approaching 0 of f of x plus h times the limit with h approaching 0 of g of x plus h minus g of x over h plus the limit with h approaching 0 of g of x times the limit with h approaching 0 of f of x plus h minus f of x over h. And we've done all this work, and the question would be, well, why? Well, through this manipulation, something interesting has happened. Notice now that this expression should be recognizable. The limit with h approaching 0 of g of x plus h minus g of x over h. You should recognize that expression as being the definition of the derivative with respect to x of g. Similarly, this factor, the limit with h approaching 0 of f of x plus h minus f of x over h, is the definition of the derivative with respect to x of f. So, this then becomes, let's see, the limit with h approaching 0 of f of x plus h, that would just be f of x. The second factor here is g prime of x plus the limit with h approaching 0 of g of x. Hey, that doesn't even depend on h. That's just g of x. And then the second factor here is f prime of x. So, how we normally write this product rule for derivatives. We'll say that the derivative with respect to x of f of x times g of x, what we'll normally write is, and it's just sort of become the standard way to write it, we'll just switch the order of the factors in the second term and write that term first. We'll write this as f prime of x times g of x plus f of x times g prime of x. So if we have a product and we want to differentiate, we differentiate the first times the second plus the first times the derivative of the second. And this is called the product rule for derivatives. So now that we've developed the product rule, let's see some examples. All right, so we're asked to differentiate each function, and here we have the function 3x to the 7th times cosine x. So I'm going to think of this, 3x to the 7th, I'm going to think of that as my first factor, and I'm going to think of the cosine x as my second factor. Then the derivative, f prime of x, would be equal to differentiating the first factor, that would be 21x to the 6th. Leave the second factor alone, times cosine x, plus leave the first factor alone, 3x to the 7th. Differentiate the second function, negative sine x. The derivative of a cosine being negative sine. Now, personally, what I would do at this point is, now, this is the derivative. What I've expressed here is the derivative, but you would never see it written like this. You would never see this plus 3x to the 7th times negative sine x. Okay, so the most basic simplification would be to write this as 21x to the 6th cosine x minus 3x to the 7th sine x. Now, personally, I would do a little bit more with this. I would write a factored form. And if you sort of think about why that might be important, think about the exercises we've done so far, where we've needed to find the derivative of a function, and then we've needed to set it equal to 0. Well, if we have a factored form, setting it equal to 0 will then be relatively easy. So let's get in the habit of maybe doing some factoring with this. So I see that I have a common factor of 3 and a common factor of x to the 6th. So I can write this as f prime of x is 3x to the 6th by 7 cosine x minus sine x. X sine x. Why don't you pause and try these next two on your own? Differentiate each of these functions g of t and p of z. All right, let's find the derivative of g of t is e to the t times t squared. All right, and I will treat the e to the t as the first factor and the t squared as the second factor. Then g prime of t. Differentiating the first. The derivative of e to the t is e to the t. So I'd have e to the t times t squared plus, now leaving the first alone, leaving the e to the t alone, that would be again e to the t. And differentiating the second, the derivative of t squared is 2t. So then I could write this as g prime of t. I could write this as e to the t times t squared plus 2e to the t times t. What I would do is, again, factor. I would write this as g prime of t, and I notice that there's a common factor of e to the t and also a common factor of t. So I might write this as t, e to the t times t plus 2. All right, we have p of z is z cubed times the natural log of z. Again, I'll treat the z cubed as the first factor and the natural log z as the second factor. I'm not going to use the color scheme here. All right, so then p prime of z would then be differentiating the z cubed, that would be 3z squared, leaving the natural log z alone, plus leaving the z cube alone, differentiating the natural log of z, the derivative of natural log of z is 1 over z. Now, when we clean this one up, notice that I have the z cubed times 1 over z. That simplifies, and so then that's 3z squared natural log z plus z squared. And so again, notice that I have a common factor of z squared. So I might write p prime of z as z squared times 3 natural log z plus 1. All right, so those are some examples of the quotient rule. Sorry, not the quotient rule, the product rule. I was thinking ahead. So now that we've developed how we can differentiate functions that are products of functions, what if we have a function that's a quotient of two functions? And so let's talk about the quotient rule. Now, we can start off similar to how we did in the past in developing the product rule and do some funky additions and subtractions. But I think there's a better way to approach the quotient rule. And so here's what I like to do. All right, so let's let let f and g be differentiable and g non-zero, and let y equal f. Let's say y is f of x divided by g of x. All right, so what I'm going to do here is remember that my goal, right? My goal is to find some y prime. Okay, that's my goal. But I'm going to start a little differently. If y is equal to f of x divided by g of x, then this is the same as writing. So then y times g of x is equal to f of x. Right? Just multiply through both sides of that equation by g of x, and if we assume that g is non-zero, that's legal. Okay, then what I'll do is apply the differential operator with respect to x. So then the derivative with respect to x of y times g of x had better be equal to the derivative with respect to x of f of x. Now notice on the left-hand side of this, I have a product of functions, y times g of x. So I can apply the product rule. So then, y prime times g of x plus y times g prime of x. And on the right-hand side, we have the derivative with respect to x of f of x. Let's just write that as f prime of x. Now, I'm going to take this equation and I'm going to solve it for the y prime. I'm going to solve for y prime. So I've got then y prime times g of x is equal to f prime of x minus y times g prime of x. I subtracted the y times g prime of x from both sides of the equation. And now let's divide by g of x. So then y prime is equal to f prime of x minus y times g prime of x over g of x. Now this is okay, but I've got one more trick that I can use. If you recall, I defined y as f of x times g of x. So I can replace the y with that same expression. So then this is equal to f prime of x minus f of x over g of x times g prime of x, all divided by g of x. And now this is an ugly expression because I've got fractions in a fraction. I've got a complex fraction. So I'm going to use one more trick here. I'm going to multiply both numerator and denominator by, any guesses? I'm going to multiply the numerator and denominator by g of x, and that'll clear the complex fraction. And if we do this, we get that the derivative, the y prime, is then f prime x times g of x minus f of x g prime of x, so times g prime of x, divided by, now we have g of x times g of x, we'll write that as g of x squared. in the denominator. And so this is what's commonly called the quotient rule. The derivative with respect to x of f of x divided by g of x is equal to, differentiate the first, differentiate the top, leave then times the bottom, minus, leave the top alone, differentiate the bottom, divided by the bottom square. And so this is called the quotient rule for derivatives. All right, so like we did with the product rule, now that we have the quotient rule, let's see some examples of its use with some functions. So here I've got a few functions. I'll do the first one. Let's differentiate f of x is equal to 3x plus 8 divided by 2x minus 5. So this is a fairly basic rational function, and we wish to calculate its derivative. So the top, right? The top is the 3x plus 8. Right? So I'll think of that in blue. And the bottom is 2x minus 5. I'll think of that in orange. So then f prime of x would be, maybe it's a good idea to build some structure here. We're going to have 1, 2, minus 3, 4. We're going to have 4 factors in the numerator, and we're going to have something square in the denominator. All right. We differentiate the first. We differentiate the top. The derivative of 3x plus 8 is 3. We then leave the bottom alone, 2x minus 5. Minus, we leave the top alone, 3x plus 8. We differentiate the bottom. The derivative of 2x minus 5 is 2. And then we leave, and then in the denominator, we have the denominator square, 2x minus 5 square. Now, that's the quotient rule, but we're not going to leave it like that. All right, we're going to clean this up a bit. So then f prime of x would be, and what we generally do is, we simplify the numerator, either by distributing and combining like terms, or maybe doing some factoring if necessary. And we generally leave the denominator alone for these. So I'm going to distribute carefully. This is going to give me a 6x minus 15. And then being careful here, I've got a subtraction. And remember that this subtraction has to apply to the entire second term. So I have 2 times 3x, that's a 6x, so a minus 6x. And then I've got 2 times 8, that's a 16, I have a minus 16. So be careful here. That's probably the most common error in applying the quotient rule is applying that subtraction correctly in the numerator. Assuming you understand how to apply the derivatives of the top and bottom correctly, then the most common error is subtractions usually. The denominator I'll leave as 2x minus 5 squared. Alright, so then cleaning this up just a little more, f prime of x, I have 6x minus 6x, that's 0. Negative 15 minus 16, that's negative 31. So I'll write negative in front, 31 over 2x minus 5 squared. That's what I'll write. Alright, so now again, this would be a good time to pause and try these remaining 2 exercises out on your own. Alright, so we have g of t is the square root of t over t minus 6. So then g prime of t. Alright, the derivative of the top, the derivative of the square root function is 1/2 t to the negative 1/2 power. Recall that the square root of t is the same as t to the 1/2, so then applying the power rule. Okay, now I leave the denominator alone. T minus 6 minus. Leave the top alone. I'm going to write this as a t to the 1/2. Differentiating the bottom. Differentiating the t minus 6 is 1. And then we have the denominator square. T minus 6 square. And I should mention that it's very tempting to try and reduce out maybe the t minus 6 here, or in the previous exercise, maybe try to reduce out the 2x minus 5. But we can't, because remember that to do that reduction, we have to have a common factor over the entire numerator to reduce with the factor in the denominator. So we cannot divide out that t minus 6, although it's very tempting, isn't it? All right, so let's see what we can do here. So what I would notice here is, and one way to simplify this is, it doesn't look like there's any common factors, but I do have a common factor of t. I have t to the negative 1/2, and I have t to the 1/2. And so what I'll do here is I'll factor out the lesser exponent. So I'll write g prime of t. In the numerator, I have t to the negative 1/2 power times what? I'd have 1/2 of t minus 6 for the first term. Now, if I factor out a t to the negative 1/2, then I have a minus what? T to the negative 1/2 times what would give me t to the 1/2? Well, negative 1/2 plus 1 is 1/2, right? That's how exponents work. So I'd have t to the negative 1/2 times t to the first in the numerator. Would then give me the t to the 1/2. And then I've got a t minus 6 square still in the denominator. And so then if we wanted to, we could have even factored out the 1/2, but I'm just going to leave that alone right now. So I've got g prime of t. I'll write this as t to the negative 1/2 times, let's see, 1/2 t minus 6 minus t. 1/2 t, distributive property, 1/2 t minus 3, because half of 6 is 3. And then I've got a minus t. So 1/2 t minus t, that's a negative 1/2 t, and then a minus 3 over t minus 6 square. So that would be one way to write it. It's not the only way to write it. We could have factored out the negative 1/2 as well. We could have, we can bring this t to the negative 1/2, we can drop this to the denominator. So we could do something like this, right? We could write this as negative 1/2 t minus 3 over root t, right? Because t to the negative 1/2, that's the same as the square root of t in the denominator, by t minus 6 squared. Or we can multiply both numerator and denominator by 2 to clean up that fraction. And so that would give me negative t minus 6 over 2 root t by t minus 6 squared. So there's often more than one way to write these, and so we've got to be careful. If you're checking your answer to something using a website or using a textbook, many times you'll have the correct expression, but just in a different form. Okay, so be aware of those sorts of situations. All right, what about this other exercise here? We have p of z is z to the 5th over 9. I hope you didn't use the quotient rule here. I really hope you didn't, because this is not new. Z to the 5th divided by 9 is the same as writing 1/9 times z to the 5th. And so its derivative is really easy. P prime of z would be 1/9 times 5z to the 4th, which is equal to 5/9 z to the 4th. I hope that's what you did. That's the simple approach for this exercise. Now, if you did apply the quotient rule, you should have gotten the same expression. Let's see that. If we apply the quotient rule, so then p prime of z, applying the quotient rule, that would give me let's see. I would have, differentiating the first, I'd have 5z to the fourth, differentiating the top, times leaving the denominator alone, times 9, minus leaving the top alone, z to the fifth, and then the derivative of 9 is 0, since 9 is a constant, and then I'd have 9 squared in the denominator. So that gives me 45 z to the fourth minus 0, so just 45z to the fourth, over 81, which is 5/9 z to the fourth. Which way was easier? I hope you can look at that and say, gosh, that first approach is easier. There's less chances for errors in that first approach. And so, generally speaking, you always want to make sure before you have to use the quotient rule. Is there a way you can manipulate the expression to rewrite it in a different form so you don't have to use the quotient rule? Because the quotient rule has several places where you can make errors. And in general, I always recommend using the least amount of steps possible, because each step, there's a chance for an error. Alright, so now that we've developed the product and quotient rules and we've seen some examples of their uses, I'm going to stop this video and we'll pick back up with some applications and some more rules for some trig functions. Alright, so let's stop here and I'll see you on the next one.